Hey guys, how's going? How is everyone doing? Welcome to episode number 6, Quantum Programming Livestream. Today we are going to play a little bit with quantum adiabatic computation. Maybe let me know in the chat if you can hear me clearly, because I had some minor technical issues while setting up as usual. That's why I'm tiny bit late. And if not, then I guess we can just get it started. So let me switch a scene to my editor, and I will pull up some cool figures maybe while I pour myself some drink. Maybe this one. This is a Pokemon figure from my blog, which is also about quantum adiabatic computation, which was a bit bigger, but it's fine, it's good enough. So before we start, oh hi Mike, how's it going? Welcome, welcome. First time here, I guess. How are you doing? So guys, take your time and pour yourself something delicious to drink. That's what I'm about to do. And then we just get this quantum adiabatic computation going. And feel free to write a few words in the chat. How are you doing? How's your weekend so far? Both of you guys are in Europe, so I guess it's early there, or quite early. Still morning, I guess. Like here it's 5 p.m. Already feeling sleepy. Yeah, it's actually happy hour. That's my happy hour. That's what I do. Alright, let's wait for this phone to fall down and get this thing started. So on the figures you see little Pokemon town maps that I optimized, so they could be translated to into graphs, and on those graphs we can solve various problems such as minimum vertex cover, maximum independent set, etc. And those problems just happen to be equivalent to the problem of finding the ground state of a quantum system Hamiltonian. And that's what we are going to do today. But I think it's just too much to cover in one session. So I might make another quantum adiabatic stream if people will be interested, of course. So let's just talk about this. No equations. Let's just relax and talk a little bit. Pull up some pictures. Let's open the Pepsi Man. And also let's open the Santa. Should be Santa somewhere here. Okay. So if you just... oh, hold on. My drink is ready. So cheers to the quantum adiabatic computing. Yeah. Oh god, I really needed that. Okay, so this whole quantum adiabatic theorem is actually about the fact that the system will naturally preserve own ground state if the transformations are slow enough. So think about it in this way. If Pepsi Man is a quantum state, if Pepsi Man is a quantum system, then its ground state could be, for example, a can of Pepsi. And if Santa is another quantum system, its ground state would be a can of Coke. And now, according to... Yeah, cheers, Mike. Santé. And according to quantum adiabatic theorem, if you transform maybe actually the other scene is better. If you transform this Pepsi Man into Santa slow enough, the can of Pepsi would follow this transformation and it would turn into the can of Coke. And if this transformation is too fast, the can of Pepsi could end up something different than can of Coke. It could become something which is not the ground state of Santa. It could become a can of Mountain Dew or superposition of different cans of different beverages, whatever. The point is that you can transform systems into different systems and their ground states would just follow this transformation. And that's very interesting because for some systems it is very easy to find the ground state, and for some cheers John, Santé. And for some other systems finding the ground state is very difficult actually and be hard. So you could use this quantum adiabatic theorem for your advantage and start your system in something for which the ground state is very easy to predict, and adiabatically transform this system into something complicated, and you would obtain the ground state for free, let's say, because it would just follow. So how about we do it? Let's play with quantum adiabatic computing. Just open a... Well, we have two Pepsi Men now. Just create a new file. Solutions episode 006.py. So this is just introduction. We will not really solve any real problems. Let me just close this Pepsi Man because it kind of distracts me. Let's open maybe this. Okay, so what I will do is I will simulate a adiabatic transformation from one Hamiltonian into another Hamiltonian, and I will repeat this process with different speeds and show you that if the transformation is slow enough, we will end up in the ground state of the final Hamiltonian. So let's get it started. As usual, we will probably need NumPy and also some stuff from Qtip, because in this live stream we only work with Qtip. Qtip is the best. Import. So to make states we will need basis. Our two Hamiltonians are going to be sigma x and sigma z. And we will not need tensor because we will just work with single qubit today, but we will definitely need expectation value. And I guess that's it, not sure what else. Oh, and MS solve. MS solve? Yeah, MS solve. And okay, so our initial Hamiltonian is going to be sigma x, and our final Hamiltonian is going to be sigma z. And then there will be a Hamiltonian which is between them, that is parametrized by time, that gradually turns from sigma x into sigma z. So let's just define it. So this is the Hamiltonian at any time, and it has two time-dependent terms. It has the h0 parametrized by a lambda expression of time and some arguments which we will ignore. And that will be, so this one will decrease. So that is going to be 1 minus time over some overall time evolution period, which let's define immediately tau, the Greek letter tau. Let's make it like 25. Let's make it 1 or 0.00, whatever, some small number, because we will not want to end up in the ground state initially. So that's H0 that is decreasing. Now we need HF that is increasing. So I just make it lambda such that increases T arcs. So this is going to be just T over tau. So it increases from 0 to tau. So this is our Hamiltonian. Let me just pull up my cheat sheet because I'm very confident I will just forget stuff, just to see if we are on track. Okay, so we will begin in the ground state of the initial Hamiltonian. Yes, sorry, just looking for the right cheat sheet. I'm totally cheating, guys, as usual. Okay, so the ground state of the initial Hamiltonian. This is our initial state, psi 0. This is going to be the minus state, right? Because it has energy of -1, psi m, and let's just define it here. So psi m equals 1 over square root of 2. Here's a challenge for you guys. Try to find a moment when we actually don't need NumPy. Two-level system 0 minus, because it's a minus state, basis two-level state 1. So that's all we need for the initial state. And we will also need to perform some measurement. So let's just think. We will need, at each moment of time, we will want to know what is the energy of the entire system. We will also want to know what is the exact energy, so that we know how our energy compares to the exact energy, so that we know how adiabatic we are. And we will also want the expectation values of the ground state of both Hamiltonians, so that we can actually see if we reach the ground state or not. So let's do it. So let's make a measurement function, which usually just takes time step and a quantum step. Sorry, time step and a quantum state. So we will measure the expectation value of minus, expectation value of, well, the ground state of sigma z is going to be 1, so expectation value of 1. And we will also measure the overall energy of the system, measurement 3. So for that, let's just use the fidelity, which is absolute value squared, as usual. So psi overlap with psi minus, which measures how much of psi minus is in psi. And we repeat the same for the 1 state. Let's measure how much 1 is in whatever we are having here. Overlap with basis to 1, right? Is that okay? I guess it's okay. This one is tricky. This one is the energy. So, oh, hi, Amiel. Welcome, welcome. My drink choice of today is Guinness. Cheers, man. Glad you joined. So, for the energy measurement, this is pretty tricky, actually, because as you can see, this is a time-dependent Hamiltonian. It has lambda expressions inside of it, which depend on the time step. So in order to perform a measurement at specific time step, one would need, which I'm copying actually right now, one would need a evaluation of this Hamiltonian at particular time step. So assuming we would have ht, we can take the expectation value of it, given the quantum state psi at time t. So the only thing missing here is actually how to get this ht. And for this, there is a special function in QDIP, which I'm going to paste because I just can't remember this name. QObjectListEvaluate. So what QObjectListEvaluate actually does is it turns this, which is general for any time step, into an age, which is evaluated at particular time step. Let's just not forget to import it from Qtip. And the way you use it, you just provide a quantum object, which could be a state, could be an operator, anything you like. So we just put h here. We give the time step at which it has to be evaluated, and it also accepts argument, but we don't have any. So let's just put empty dictionary. And this is the measurement we are having. Let's just return it. And this is for every time step. So this is M1, M2, and M3. Oh, by the way, thank you, Emil, for suggesting this topic. It's actually Emil who just written in the chat. It was his idea his request to do quantum adiabatic computation. And it was actually very cool because that's interesting enough to actually do something that, does something. And we have barely enough tools already built to actually do something like that. So yeah, good call. Alrighty, so before I actually do anything further, how about we just try to evaluate it so that we don't have like so many, syntax errors to fix once entire thing is done. Oops, I guess we should rotate the windows. I like to just do it the buffer way. And that's it. For some reason, Emacs doesn't want to automatically evaluate my bash profile, so I'm just doing it manually, which is fine. Yeah, man, you are the only one who suggested it. I mean, I don't really get many suggestions, to be honest, so it's another reason why I appreciated your suggestions so much. So, message to you all, feel free to suggest things. I will be happy to follow your suggestions. Okay, we are in the graphics directory, which is not good. We should go to solutions. And let's just evaluate this episode 006.py, see if I made a boo-boo there or not. Okay, it's goodies. Traceback, line 3 from Qtip, import this thing. Cannot import, oh yeah, because this is actually me solve. Master equation solve. Such a politically incorrect name, the master equation. Oh my god, those people, how dare they? Alright, it's goodies, it's evaluating. So we are ready to do our time evolution. So let's compute some time steps, which is like basically all the time steps, and also in case if we need the derivative, let's also get dt. NumPy linear space from 0 to like tau, right? Let's make 50 of them. I think that's enough resolution for a smooth plot. Let's return the time step just in case. True. Oh god, the naked strips is here again. We are doing quantum programming here. We are not interested in your naked stuff, okay? Please go away. I guess that's it. We can just do this now. MeSolve. MeSolve stands for Master Equation Solve, but I like to call it just Solve Me. Like imagine this Hamiltonian saying, "Solve me, please. I want to be solved. I don't want to remain unsolved." So we give it the Hamiltonian. We give it the initial state. We give it the time steps, and we give it the measurement function, which is measurement. And this is enough to just run the simulation. We can extract the measurements into separate arrays like this. So we just make result.expect, which stands for the expectation values, and we want it as numpy array because that will allow us to do the transpose of that. So otherwise we have nested lists, which are not cool. And yeah, and this is yeah, let's take the transpose of this, and then we do ms0 measurement 0, m0, ms1, which is the expectation value of 1 for every time step, and finally the energy, which I will call the ms2. So this is what we measure during the time evolution. And I think that's enough to just demonstrate how things work. So let's just plot it. We have a special function for that from the last stream called plot time evolution, which takes time steps, fidelities, and potentials, which here are the energies. Let's call it AQC1, whatever. The name doesn't matter. File name equals res. Not pi, PNG. PNG, please. So let's make those fidelities and energies. So fidelities here will be the expectation values of those relevant quantities. So the expectation value of the minus state and the one state, which are the ground states of the composing Hamiltonians. So this is ms0. So let's just call it no, hold on, this is 1, right? No, this is minus psi at moment t. Okay, and also let's make well, the one state, of course. So this one's going to be 1 psi at moment t. So this is what we need for fidelities, and energies. It's just one energy here, one energy, which is the actual measurement, because we don't really yet have the exact energies. So for that, this is just going to be the ms2, the last measurement. Let's just label it quite extensively. So this is the expectation value, right? This is the expectation value of the Hamiltonian. So this is going to be psi at t, and this is a nice sandwich of quantum states with h at t in the middle. Delicious. So let's try to run it. I'm going to run it now, and let's see what it gives. The total time evolution time is really small. It's like less than 1/1000th. Red step. Oh yeah, the underscore. All right. Plot time evolution is not defined. Impartiable. From plotting, import, plot, time, evolution. Alrighty. Please behave now. Do we get something nicer? Yeah, we do. We do get some results. So a moment of truth. Okay, but I wanted them in different order. Shell. Okay, so what do we have here? Is this right? So starts at -1 energy, goes to 0. There is expectation value of minus for the whole time. I guess the total time evolution might be just too short to complete it. Let's make it slower and see if it tends to the 1 state. So it's just time evolved for single unit of time. I really love dimensionless units, guys. Dimensionless units are the best. See if it will curve it just a little bit. Yeah, see? So now oh, the LaTeX is broken. Forgot the... Why the LaTeX is broken? It's fine. Oh, I forgot the dollar signs. That's why I felt it's odd. Terribly sorry for this, guys. I deserve a punishment, I guess. No beer for 1 week. That's severe. I'm so into aesthetics, I'm willing to rerun this entire simulation just to have the LaTeX properly. Yeah, now it looks nice. So, you can see that before, minus, fidelity of minus was just a straight line. It never left the minus space. Naked HD looks really interesting. Don't click this link, please. It might be something dangerous there. I take no responsibility for whatever happens to a person who clicks on the links posted by bots in my stream chat. Okay, so the line is no longer really curved, as you can sorry, it's no longer straight, it starts to get curved. So because we do it slower, we got a bit closer to the 1 state. So we are more adiabatic than before. So how about we got even more adiabatic? Let's go even slower. Twice slower. Do it slowly. Then I think about Dune again. Slow blade. Alrighty. Yeah, we actually... So now their fidelity swapped. So actually it becomes more likely to measure 1 than minus, which is pretty neat, but we don't yet reach the energy of the ground state of sigma z. Like, as you can see in the potentials plot, which should be energies, we are approaching minus 0.06, and the energy of sigma z, the ground state, should be minus 1. So let's do it even slower and see how much closer we can get. Yeah, that looks even better. So we are almost reaching -1 energy at the end. The curves definitely swap. Like, it becomes almost certain we would measure 1 at the end, which is almost correct. Like, as you can see, the orange curve is really, really close to 1, so it's almost certain that will be measured. So let's just go even slower. 8 units of time. See what it gives. So we definitely reached the energy of -1, and at least to me on this plot it looks like measuring 1 is certain. So that's the adiabatic computation. You transform Hamiltonians and the state follows the system if you perform this transformation slow enough. So sorry. So let's just talk about another thing. So here we cheat a little bit because we know what's the energy of the ground state of Z, but and also we don't really know how close we get to the actual excited state. So how about if we include one more, like two more curves in the potentials plot showing the exact ground state for the Hamiltonian at this particular time and also the exact excited state so that we know how closely we actually approach to closing the spectral gap between those two energy states. So for this, we would need to actually compute the energy spectrum at every moment of time. And let's do it using those really cool, neat Python one-liner expressions, sorry. So, spectrum. Energy spectrum of H definitely is going to be a list of values, right? And we can actually compute the eigenspectrum, but it needs to be a Hamiltonian evaluated at a particular moment of time. It cannot be a time-dependent Hamiltonian. So we will definitely need all the moments of time, right? So for t in times. And now we need to find a way to actually compute the energy spectrum at this particular moment of time. And we already know that we can do it from QObject, list evaluate function. And we will provide it with time-dependent Hamiltonian, moment of time t, which we already have, and some parameters that we don't care about at this time. So that's already sufficient to actually get the spectrum, but we would like to be able to separate each curve into separate list. So let's do the same trick as we did with the actual measurements and turn it into NumPy array. And let's transpose it. So now from that we can get the ground state at every moment of time by just getting the spectrum of 0. So the first sub-array, and the excited state spectrum, the first sub-array of the spectrum. Let's just include them here. So this is going to be ground state. Let's just call it GS for the ground state. And this is going to be the excited state. Let's just call it EX. So, and let's also go back to do it like super fast so that we can see the line not covering actually. So I think we started with something of this order. Almost instantaneous change. Okay, so let's run it and see what it gives. Tuple object is not callable. That's sad. It looks like we are facing a debugging exercise here. So which line is it? 46. Let's display some lines. What? Why you don't want to show me lines? Okay, now 46. Here. The apple is not callable. Okay, I guess I just forgot a comma. That was easy. Come on, God, is that all you have to challenge me? I dare you. Okay. Value error. What x and y must have same first dimension. Guys, looks like it's another debugging exercise. But they must have the same dimension. Like, they use the same time steps. That's the problem here. Oh! I just evaluate Hamiltonian, but I don't actually get the energies. This is just like a list of Hamiltonians, and I'm trying to plot it. Okay, so dot eigenenergies. Booyah. Try that. Let's see. Damn, this thing works. Yeah. Should I open another one? I think we're close to done here. Okay, we got it. So, the bottom plot, the potentials, we see now three curves. The green one is the excited state, orange one is the ground state, and the blue one is whatever the energy occurs during our time evolution. So as you can see that at the beginning, the blue curve and the orange curve sort of overlap. So at the beginning we sort of go slowly enough to remain on this ground state, or at least very close. But at some point we are just going way too fast and they just diverge, and we end up in different state than the ground state of the final Hamiltonian. So for that reason, let's just go a bit slower. So it was around 0, right? The energy was around 0 at the end. Still around 0, not slow enough. Even slower. Single unit of time. That should do it. That should make some sort of difference. Alrighty, well, it's a bit lower. It's below 0. Still far away of -1. But we can already see the impact on the fidelities. We can see that, well, minus is still more detectable from 1, but there is actually detection of 1 is no longer, it's no longer random 50-50. It actually becomes, 1 becomes more probable than 0, which is a good sign. So for that reason, let's try to go even slower. Okay, we reach -0.05 energy, and this is more or less the threshold from what we can see when the fidelities actually swap. So the 1 is more detectable than minus at this stage, but minus is still quite detectable. So if we do our quantum computation like this, we are not certain we will get the solution to our problem. So let's go even slower now. The more slow we go, the more blue curve should overlap with the orange one. My drinking is definitely not adiabatic here. It's quite fast, actually. Okay, so yeah, 1 is almost certain to be detectable, but not completely. It's very close to 1 fidelity. And the blue curve already has similar shape to the orange curve, but they don't really overlap. So the time evolution goes a bit faster than required. So the blue curve is slightly above the ground state, but eventually gets really close to it. So for that reason, let's increase the time evolution one more time. And now we would expect them to just cover exactly. So let's do it. Done. Okay, just one today, guys. Need to focus. Alrighty, so 1 becomes certain to be detectable, reaches 1. I'm not sure why minus is not really... I mean, it's like 50-50 measuring minus in the x basis. Because you can always change the basis, so if 1 or 0 are certain, I guess plus or minus should be like 50-50%. So that's fine. The blue curve sort of overlaps with orange curve, but I think I can see some difference there. Just to be safe, let's increase it even more. Probably the expectation value of minus would reach exactly half now or next time. Let's see. What you got there? Yeah, actually, yeah, they definitely overlap much better. And the expectation value of minus got even closer to half. So, do you guys want to go even slower? Let's go even slower. Last time. Alrighty. So I see, yeah. So 1 becomes certain at the end. So it gives you the ground state. And minus is 50-50, I guess. I guess my contact lenses are not good enough to see this difference. But the spectrum, like, to me, overlaps good enough. So I guess we're done here. I guess this result satisfies me, so let's just stay with that. So before we actually finish, let me show you what we are going to do next time. So next time, I think about doing this Pokemon problem maybe. If you feel urgent to see it before next stream, you can just check my blog because it's solved there. Well, basically the problem is finding the maximum independent set of those Pokemon Poke Centers and gyms. So I don't remember exactly what it was about. Like making it. I think it makes sort of. Yeah, you wouldn't want to have 2 gyms next to. You would want to minimize the times when gyms are next to each other without a Poke Center. You would like to sort of distribute them as well as possible. And this problem happens to be NP hard, actually. And also, it maps really well to quantum adiabatic computation. Let me just open the other one. It actually maps really well to... damn, I opened the same one again. It actually maps really well to quantum adiabatic computation. Wait, did I open the same file twice? Whatever, forget it. You can see it at the beginning of the recording. So, yeah, we can, maybe next time we can do this problem. So I would start by just brute forcing it, just write a little recursive Python function that would find all the best solutions, and there exist exactly 3 solutions here. And after that, we would maybe make a Hamiltonian that corresponds to the solution. The ground state of it would be the solution. We would just adiabatically find it. So that's one of the ideas, but still have to think about it. I'm not sure if there will be more streams in 2021 because it's almost the end of the year and it's quite busy and so other things to do. So I will still think about that. But if not, we might see each other next year actually, which is still pretty soon because it's December already. So yeah, that's it for today. Thank you guys for joining. I hope you liked it. I'm glad we did not have major technical issues today, which is surprising. And stay safe and take care. Cheers. Bye. Stay tuned.